Today I'm going to talk about introducing HDF5 with Cabana. And basically Cabana is a performance portable library used for particle-based simulations. So that includes molecular dynamics, particle and cell or n-body cosmology. It has, when we first started to work with Cabana, the Cabana team, it had the option of doing silo output. And for silo, they use the BDB, which is the default in, well, the native silo backend. There's you can also use an HDF5 backend in silo, but they weren't enabling it. They were hard coding it to use the native format. You can find the source code and everything I showed today on the GitHub on there in the Cabana repository. So with that, I'll just go to the source code so we can kind of look what is involved with integrating HDF5 with COCOS is what their main tool is that they use to do, for example, running on GPUs. And so we tried to integrate that into how we do the HDF5 because HDF5 doesn't have a, well, we have a VFD that can do direct from GPU, but for this case, we don't use that, and we just copy back from the GPU memory back to the CPU memory using COCOS. So they have a function that writes the time step. So we introduced a structure for configuring the various HDF5 parameters. So if you go and look up in that structure, right now it's kind of a rudimentary, is you can switch on whether you want to do collective or independent IO, whether you want to align the file, do alignment and the threshold and alignment values. And then metadata is turned on by default, but you can turn it off if you want. Since then, I have another PR that have the option of running with subfiling, and I also have whether to turn on or off field values. But currently in the main repo for Cabana, that doesn't exist. So that should, after I get that PR approved, it should be in there. And then you have the prefix of the file, the HDF5 file, the communicator, the time step that you're writing, and the time if you want to, the actual time step. And then the node local, that's the number of nodes on that node, that rank, the number of particles in this case. And then you have the coordinates of those particles. And then you have the fields that you want to write as well at those particles. And then you have the, you can then prefix the file names. So we do that with an so for this case, we create an HDF5 file, and then we also combine that with XDMF format. So we also at the same time create the header file for the XMF files. Then you have your standard HDF5. After that, you have you call your MPIO driver. And then for this case, if you have version 110 HDF5, you can turn on collective, which is the default, collective metadata. You can also do, if depending if you want to alignment, you can do the alignment, and then we create the file itself. And then we want to reorder from the GPU. When it copies it back, we want to reorder that into a contiguous memory, since that's what we're going to use. So we use COCOS to do that. And so we set the coordinates view for COCOS, and then we do a loop that will combine those slices on the GPU memory into, well, this kind of sets up COCOS, and then the actual mirror of the memory is done here, create the memory view copy. So this actually copies from the GPU memory into the CPU memory. And so at the end, you'll have this coordinates view, and then we pack that into the pointers for each. So we have the X, in this case, it's the X, Y, Z coordinates. And then we also want to find out how many particles that each rank is going to end up writing. Since we do a hyperslab selection for each rank, and each rank will write its part of the particles, we have to find out how many particles each rank is going to do. And for that, we just do an all reduce. And then we set up the parameters for the hyperslab selection. So we set up the offset that each of those will have, and the offset in the file, in the HDF5 file itself. And then in this case, the actual size of the fields, that the coordinates that you're writing. Then you create the data space. And then you can set that if you want to do collective or independent IO, you create the data space itself, then select the hyperslab. So this is all standard HDF5 with writing a hyperslab. And then we want to find out which type of data we're writing. And then we also create, so this is for the XDMF header file, because we want to tell it, we want to include what data type that is using. And then we finally write the fields itself, the data itself. Or sorry, let's see where we write the data. Right there, sorry. So earlier we write the data itself, and then we close the file. So we close the time step, and then we go ahead and just have rank 0 create the XDMF corresponding XDMF file with that corresponds to that HDF5 file. And for that, we give it the data type. I'll just briefly go over what the header file looks like for creating the XDMF. So it's the standard, you have your standard header stuff that you have. The grid describes the topology that you have, the header geometry. Then you have the main body. So this is whether it's this is for usually for the fields. So you can have a matrix field, a vector field, and a scalar field. So we use those. You'll see them later that when we output the fields for the particles, they can be either of these. And then we just create the header. We create then whether it's a scalar, vector, or matrix, and then just end the header. So we have all the 0 processor do that. We don't have all the ranks doing that. After that, then we want to go on to do the fields. So depending on what fields are passed in, you select whether you're doing, let's go back up, for example, this is be a rank 0 field. So again, you pass in the local and the global coordinates, or the number of particles, the offsets. And again, you have COCOS copy from the GPU memory, in this case, to the CPU memory. And then we find out the type ID that we're writing, since we're not passing that in. We get it from what type of variable it is. That's what H5D traits does. And then we again create the hyperslab as we did for the particles. But in this case, it's just a scalar field rank. And then we again determine then we write down all that data. So it's fairly straightforward. And then we assign that entry that corresponds to that field in the XDMF file. We do the same thing for the rank 1. So it's all basically the same, except now we have different offsets. We have an array that we're writing. So each rank will write its own array. And then finally, we have a matrix. So I think this is handled 9 by 9. And you again write it. You create the hyperslab for each to rank, and then you write the data, and then you create the entry in the XDMF file. And that's basically all we had to do to get HDF5 working within Cabana and working with COCOS. They did a lot of heavy lifting with the COCOS part to get it into a usable format that we could use in HDF5. So I thank them for that. So that's basically all you really had to do to get that working in Cabana. Is there any questions about that? Like what kind of fast, and it's all on GitHub if you want to reference it. Okay. So I'll go back to, I can take questions later after the talk. So we want to do some performance benchmarking. And for that, we use a proxy application for material point method. And this is again on GitHub. It's part of it's the same Cabana directory, except now it's a separate repo. And we use this, they kind of pointed us to this test case to use to do performance analysis of using HDF5 with theirs. So for this case, we did 5 outputs. Essentially, I did 5 time steps and then output each time step. And I did weak scaling, so I increased the number of the number of particles as the number of ranks increased. So I ran it on 120. So I ran it on Summit, so it's 42 ranks per node, and I ran for 128 nodes, 256 nodes, and 512. And you can see the file sizes went from 75 gigabytes to 250 gigabytes. I was trying to really run a little bit bigger, but when you get to the 512, it was having memory issues. So I scaled it back to these file sizes. Now, if you were to look at, when you do the silo output, it's kind of like a file per process situation when you do the silo output. So in this case, you would, for 128, you'd create 4,000 some silo files, and then of course the worst would be at 512, you create 8,000. So that's over five time steps. So obviously, if you have more output dumps, the number of files is quickly grows. So that's one disadvantage of using silo as the output. So now I've compared, let me make it bigger. So I compared silo DB, that's the silo output, with the writing. This is now with subfiling enabled. I didn't compare it with the others because these are pretty expensive runs at this scale on Summit. So we didn't use it by allocation. So I just compared it to using with subfiling to the GPFS file system. And then I also compared it to writing it to the node local file system. And then if you want to get and I use the default subfiling. So it's 1 subfile per node. And I also we found that the alignment on Summit is good for 16 megabytes. So both the stripe size in subfiling is 16 megabytes, which matches the alignment in HDF5, which was also set to 16 megabytes, and the threshold was 0 for that earlier, which I showed. And if you want to have an HDF5 file in the end, there's a tool that we call H5 Fuse that fuses the subfiles back into a single HDF5 file. And for that, you can so if you wrote to the GPFS file system, then it's going to create one single HDF5 file using those subfiles that are on the GPFS, and then essentially combining them onto the GPFS. Or you can then use that tool. If you wrote them on the node local storage, it would essentially take those from the node local and then write it to the GPFS system. So the first case, the blue here is using silo. So this is a log scale, mind you. So this is the right time per output dump. So there's 5 output dumps, and these are the statistics for each of those, the min and the max that each took, and some outliners. So the number of ranks was all the way up to 21,000. So you can see that silos around here, which scales pretty good. Of course, you kind of expect that since it's a file per process essentially. So they get really good performance actually. Then if you do subfiling to GPFS, this is the next one here. It does fairly well as well. There's still a couple outliners, but it does on par with what you're getting with silo output. And then if you do subfiling to the node local storage, it's very good. And you don't see this. I mean, this is a little bit of variation, probably due to other people using the system. You can kind of eliminate that variability with using node local storage, since there really shouldn't be any competition. Now, if you want to then combine those subfiles back in, so these two or the next ones is how long it took to combine those files. So roughly a little more than 10 seconds. Same with this, and then this took a little bit. There's some reason this took a long time on the GPFS system. But going from node local to GPFS was pretty good. It was on par with what we saw with the other ones. So that's really good, I think. And you can kind of hide this. We haven't done it yet, but you can hide this by just opening up a thread in your application and then running in the background to fuse those files back. We're not sure yet how that impacts your computations if you go on, but so that's still, but you should be able to hide this kind of overhead for using subfiling. And that's pretty much it for what we did for Cabana. It was kind of a still work in progress. I just kind of wanted to give an update on the results. So is there any questions? Follow up on? But yeah, if I have more allocation, I will probably compare it with a single shared file, which is in the past it's been pretty bad compared to the subfiling. I mean, it's more near the 100 seconds, and it pretty much scales. So no questions. So are there any other general questions people might have?
Dana, is there anything you want to say release-wise or any other announcements to make?
Let's see. So 110 will probably go out at the end of this week, or possibly very early next, but we're shooting for the end of this week. Then I think 114.1. I haven't updated the GitHub yet to reflect the change dates for anything. 114.1, it looks like end of April. Looking to get that out at the very latest early May, because we have to get that in for ECP. And then 112.3, which will be the last version of the 112 line, we'll probably try to shoehorn in there at some point. But if that one's much lower priority, so that may get kicked until May. But we'll see. And then we should also have another version of HDFU that is based on HDF4 4216 and HDF5 114.0, and that should be out in another week or two.
I can give an update too for sunspots. So we were able to get HDF5 so we built it on Sunspot and we were running our test. We saw that with the default ImPitch compilers or Intel, essentially, it fails. But then I don't know if you've been following this, that they're able to find if you use the debug version of the compilers, then HDF5 will work. And we also were able to get the Vol Deos test mostly pass all the tests with Deos on Sunspot, except one was failing, but we have to rerun that with an updated test. It's one of the big IO tests that fails, but other than that, all the Deos Vol tests seem to be working on Sunspot.
Might want to explain what Sunspot is for anyone who isn't.
Yeah, Sunspot's the test bed for Aurora coming in on Argonne.
It has access to the Deos file system.
Mm-hmm.
Okay, so it sounds like we've got everything taken care of in this meeting. Feel free to interrupt if anyone has any questions. And next week, it looks like Dana will be up for his session. So we'll hear from Dana next. Great. Thank you, everyone.
All right.
Bye.
Bye.
Bye.